Hello. In this simulation I am using an evolutionary genetic algorithm for data synthesis to generate the data necessary to train a simple neural net using backpropagation. The simulated agents in this world have 4 basic properties: intelligence, mass, strength and vision. The values of those properties form a set of weights, which sum up to 1, comparable to a limited amount of skill points, that can be distributed onto a character. The agents compete for food using movement and combat, trying to maintain HP and regain energy. The strength property affects the probability of an agent winning a fight against another agent. Both agents involved in a fight lose HP and energy, but the loser of the fight loses significantly more HP. The mass property determines the movement speed and the amount of energy lost per tick. Heavier is slower and needs more energy to move. The vision property sets the maximum distance an agent is able to see. The intelligence property determines multiple factors that affect the training of the neural net. The constellations of intelligence, mass, strength and vision are quantized, to allow for shared neural net weights, when the agent's properties are very similar. The neural net has 18 inputs feeding into one fully connected hidden layer with 16 nodes, which then gets passed into another fully connected layer with 6 outputs. 16 of those inputs are based on vision, which is achieved by measuring the distance to the closest agents and closest food for all 8 segments surrounding the agent with a maximum distance determined by the vision property. The remaining 2 contain the current velocity of the agent. The 6 outputs are split in 4 for acceleration direction and 2 for trying to eat or starting a fight. Every brain has a certain amount of memory depending on the intelligence, to store the required input/output pairs for learning through backpropagation together with a fitness value. Since this labeled data does not exist, evolutionary pathfinding is used to synthesize that data. The evolutionary algorithm tries to simulate the agent's thought process, when trying to find out what actions to choose in the near future to get the best result. That thought process happens every 140 ticks. The amount of parallel searches the agent can perform are determined by its intelligence as well as how far in the future those searches can look ahead. To perform that parallel search, a multiverse is simulated in a small area around the agent. The genetic in the beginning of that evolutionary process is chosen randomly and consists of a vector of those 6 action outputs of the neural net for each time step. That genetic is then crossed on every iteration based on the fitness value, which is computed by rewarding distance traveled and evaluating the difference in HP and energy, supplemented with a very small mutation rate to not get stuck in a local maximum too easily. When the evolutionary search has finished, the dataset with the highest fitness value is the candidate that is used to fill the memory or replace parts of the data that the agent already had in its memory. If the replacement happens is decided randomly, using the fitness value of the new and the old memory as the distribution. That way it is more likely that a memory with higher fitness stays in memory, while a new memory is more likely to replace an old one that had a lower fitness value. The neural net is now able to train many iterations using backpropagation on every tick using that evolving memory, imitating reflection. In this experiment, I created 3 types of agents. The first one is balanced, all 4 properties have the same value. The second one has high intelligence, high vision, low weight and low strength, making it smart and fast but weak in fights. The third one has low intelligence, low vision, high weight and high strength, making it slow and not that thoughtful, while having the highest probability of winning a fight. I ran the simulation 10 times in each of the following settings. The first 10 runs simulated 40,000 ticks, using the untrained neural net weights that each agent type has been randomly assigned. The second 10 runs used incremental versions of the brain, how it developed during the training within the first 15,000 ticks, and then the latest version of the brain for the rest. The third 10 runs used the trained brain directly from the start, which corresponds to 112 evolutionary searches and thousands of iterations of backpropagation. To measure the process, every simulation wrote the state of every agent into a database every 100 ticks. The following graphs show the minimum, average and maximum amount of agents that were alive at the given tick grouped by the 3 agent types. The balanced one in blue, the smart fast one in green and the slow strong one in red. Since the agent density in the beginning of the simulation is the largest, the losses due to fights are higher in the early game, with the green ones with the lowest fighting strength suffering the most from that. In mid to late game, movement speed to randomly stumble over food has a higher impact on survival, which leads to green coming out on top in the end. The red and blue ones are going stronger in the beginning, and blue is able to come out on top of red after the first fights, benefiting from his higher movement speed, but not able to keep up with green, with all parties using their untrained brain. The simulation with the incremental versions of the brain caused the highest variance in outcomes, as you can see in the larger area surrounding the average, while the big picture remains dominated by the game's design. The final chart shows the averages of the 3 simulations in comparison. The solid line representing the average of the simulation using the trained brain directly from the start. The dashed lines representing the untrained runs, and the dotted lines the incremental brains. It turns out that the blue ones benefited the most from their intelligence, being over 1 standard deviation above the untrained brain on average over the majority of the 40,000 ticks. While intelligence did not have a significant impact on the red slow strong ones, the smart fast green ones are able to outperform their untrained versions in the late game. In the incremental and the trained case, the green incremental version outperforming the fully trained version may be the result of blue performing that much better in the fully trained case, causing more late game fights to lose for green. While intelligence did not change the overall survival ranking of first place for green, second place for blue and third place for red, all 3 types ended up maintaining a higher number of survivors over time compared to their untrained counterparts.